Let's try to understand now the gas exchange and how the gas moves through the body. And before that, we need to understand something about pressures and gases. So, as you know, and we talked already about this, that gases would move from areas of high pressure to areas of low pressure. Now, any gas in any chamber, it will produce a pressure. So here, for example, we have the oxygen, it gives 159 millimeter mercury of pressure. Nitrogen will give 593 millimeter mercury of pressure. Now, if we mix those two gases, we will get 752, which is the sum of both gases. So in this chamber, we have a partial pressure for the oxygen and partial pressure of the nitrogen. In a mix of gases, each gas has its own partial pressure. And that is how those gases would move through the body. So here, this is the alveolus. This is where the oxygen would come, and this is from where CO2 would leave. Now, comparing the pressure, the partial pressure of those gases between the alveoli and the atmosphere, we can notice that for the oxygen in the atmosphere, it's high, 160 millimeter mercury, whereas in the alveolus, it's only 104. Therefore, the oxygen would run into this area because it's moving from area of high pressure, which is the atmosphere, to area of low pressure for oxygen only. Okay, so the oxygen would come from this area from 160 millimeter mercury pressure to the area of 140 millimeter mercury. We will talk about CO2 later, but let's move with the oxygen. So in this oxygen here, now it has partial pressure of 104. Now in the blood capillaries and in the arterial system in general, we have a blood pressure of oxygen of around 100 millimeter mercury. This is enough. This is 104. This is around 100. This is enough for the oxygen to jump from the alveolus into the blood. So now we have the oxygen in the blood. It goes to the heart. It comes back to or it gets distributed to the body. And then in the cells or between the cells or at the cellular level or between the tissue, we have partial pressure of oxygen is 100. But in the cells consume oxygen. So it's always like less than 40 millimeter mercury. Remember, cells will use oxygen to burn glucose and to get energy. So they always need oxygen. The oxygen is always consumed. That's why we have less oxygen there. So here, the oxygen here is at 100. The oxygen here is at 40. So the oxygen will go to the cells. Always oxygen will go from area of high pressure to the area of low pressure. Now, as a result of burning oxygen and glucose, we will get CO2. So CO2 in those tissues is always high, 45 millimeter mercury or more. Whereas in the venous system, in the venous blood, the CO2 is around 45 millimeter mercury. Here it's more than 45 millimeter mercury. So here CO2 levels are high. Why? As a result of burning glucose. Whereas in the blood, in the venous blood, it's around 45 millimeter mercury. Here is more than 45. So the CO2 will jump from the cells to the venous blood. And through the venous blood, through the circulation, it goes back to the lungs. So now we have here CO2 in the alveoli. What is the concentration of the CO2 or what is the partial pressure of the CO2 in the lung is around 40 millimeter mercury. But see in the atmosphere, it's 0.3 millimeter mercury. It's extremely low. Therefore, the CO2 would diffuse out, would run out. Why? Again, CO2 is moving from the area of high pressure to the area of low pressure for CO2. So always the gas will move to the area of low pressure. Oxygen, the cells have low or less oxygen, therefore the oxygen will tend to move toward them. CO2, they are producing CO2. CO2 will tend to move away from them toward the atmosphere. So this is how the gas exchange in general through the body is happening. This is, you can think of it, the driving force of oxygen and CO2 transportation based on the differences in pressures. So you can think of this, what is causing the oxygen to move from the alveolus to the blood, what causes oxygen to move from the blood to the cells. And the same thing, what causes the CO2 to move from the cells toward the blood, and then from the blood toward the lung, and from the lung toward outside. And if you remember, we said that this is the external respiration, the changes of gases between the alveoli or the alveoli or the lung and the blood. This is external respiration. Internal respiration is between the blood and the tissue. And when we say gas exchange, it involves both oxygen and CO2. Oxygen and CO2. Okay, now what we will try to understand is how the CO2 transported through the system or through the blood, and how oxygen also is getting transported through the blood. Meaning here, now we understand that oxygen will jump to the blood because of the differences in particle pressure. CO2 will diffuse to the lungs because of the differences of particle pressure. But what we want to see is how this oxygen is moving through the body, how this CO2 is moving through the body. Okay, so that's what we'll try to understand, and that is the details of the gas exchange. So for this, we'll try to do some drawing. So we will draw the two areas. That here we will have the lung, okay, the atmosphere, and down here we'll have the cells, okay, and of course here we have the heart, so that transportation will happen through the heart. Also we will have, I will draw red blood cell. This is red blood cell, and this red blood cell would go through the circulation and would come out to the tissue as also red blood cell, and then which will go back through the circulation. Okay, let's talk first thing about the oxygen. Oxygen, we have it here. It will move to the red blood cell. 98% of oxygen will be transported through the red blood cell. So for oxygen, we have two ways of transporting it. The bulk of it is binding hemoglobin, okay, and traveling within the red blood cell. And then there is around 2% or less, sometimes from 2%, diffuse to the plasma. So just the oxygen will be running around in the plasma. So this, it will run with the fluids of the body to the cells, and the cells will take it. This is only around 2%, but the bulk of it will be through the red blood cells. So inside the red blood cell, what's happening? What do we have? We have hemoglobin. Oxygen will bind hemoglobin, and it will give us oxyhemoglobin, HbO2, and we will get a hydrogen ion. So this, as you know, oxyhemoglobin. So now this red blood cell will move through the circulation. Once it arrives at the cellular level, we will reverse this equation. We have here oxyhemoglobin. It will bind a hydrogen ion, okay, and it will give us hemoglobin and oxygen, and this oxygen will go to the cells. Okay, so this is how we are transporting oxygen with hemoglobin. We'll go into the red blood cell, bind hemoglobin, so we get oxyhemoglobin, move through the blood. Once around the tissue, we will reverse the reaction. Oxyhemoglobin, bind hydrogen ion, get hemoglobin back, and release this oxygen. This oxygen will diffuse to the cells. Okay, so this is for oxygen. Now for simplicity, I will redraw everything and we will talk about CO2. But in reality, both the processes, this and what we will see next, are happening at the same time. So here again, we have the lungs, we have the heart, and down we have the cells. Also we have the blood cell that will move through circulation. It arrives at the cells, okay, and then moves back through circulation. Now for CO2, it's more complicated than the oxygen. For CO2 transporting through the body, there are three ways. First one is around 7% of CO2 diffuse to plasma and therefore transported as CO2. What does this mean? It means that those cells will produce CO2. The CO2 will go through the plasma, okay, through the circulation. Once it's around the lungs, it will diffuse to the lungs. This is 7%. Okay. The second one, around 25% of CO2 binds hemoglobin and therefore transported through the red blood cells. Now, CO2 with hemoglobin binds the protein, binds the globin. The oxygen will bind the heme, if you remember this from the blood. Oxygen will bind the heme, whereas the CO2 will bind the globin part. So this is 25%. So here, we'll get CO2, will move into the red blood cell, will bind hemoglobin, okay? And this will give us carboaminohemoglobin, if you remember this from the blood. Carboaminohemoglobin. Carboaminohemoglobin. This red blood cell will move through the circulation as normal. Once it's around the lungs, we will reverse this reaction. We will have here HbCO2, okay? This reaction will break down into hemoglobin and CO2, and this CO2 will move to the lung. And we said this is around 25% of CO2 transported through the body by binding hemoglobin. The third way, which is the most challenging way to understand, is that, which is the bulk of CO2. We're talking about maybe 70% of CO2 transported as bicarbonate. This bicarbonate, it means what does this mean? It means I need to convert CO2 into bicarbonate. Okay, I need a way to convert the CO2 into the bicarbonate. This CO2 is here. This is the C, and those two oxygen are embedded within those three oxygens. Two of those three are coming from the CO2. So from where I will get the hydrogen and another oxygen? Simply from water. I will get water, bind CO2, and this will give us carbonic acid, H2CO3. Okay, this is called carbonic acid. And here we will have an enzyme. There is an enzyme that makes this process. Now later, this carbonic acid will break into hydrogen ion and bicarbonate. So the two steps of converting CO2 to bicarbonate are first binding water and CO2, getting into carbonic acid, then breaking down carbonic acid into hydrogen ion and bicarbonate. So this reaction, you can actually write it in one line. It's water plus CO2. It gives carbonic acid, which can be broken into hydrogen ion and the bicarbonate, right? So what we want is this bicarbonate. Therefore, this CO2, in order to have this process, in order to happen, needs to happen inside red blood cells. Why? Because of this enzyme. This equation can happen, this binding of water and CO2, it can happen in the plasma, but inside the red blood cells it's much faster because of the enzymes. So for this, the 70% or the bulk of those CO2, to get them into bicarbonate, it means I have to take CO2 into the red blood cell. There we will have water, which will give us the carbonic acid, which will get broken into hydrogen ion and bicarbonate. Okay, now this bicarbonate will get diffused out to the plasma. So technically here, when we said transported as bicarbonate, we should have added in the plasma, because that bicarbonate needs to move out from the red blood cells into the plasma, and from there it will go through the blood all the way to the lung. Okay, now this movement of this bicarbonate toward outside, toward the plasma, it means what? It means I'm putting a negative charge, I'm taking a negative charge from inside and putting it inside. So technically I'm adding plenty of those negative charges. Therefore I need to take some of the negative charges in the from the plasma. Therefore there will be a pump. This pump is called the chloride pump, that with every bicarbonate moving out, I'm bringing chloride ion in. Okay, so this chloride pump is very simple. It means I'm taking this chloride ion into the red blood cells because I'm depositing in the plasma a bicarbonate ion. Okay, and this later we will get reversed. When we are here, we will get it reversed. Okay, but the bulk of it is done now. CO2 plus water, carbonic acid, which will be broken into hydrogen ion and bicarbonate. Bicarbonate has to go to the plasma, and in order for it to go to the plasma, I have to bring a chloride ion inside. Okay, so now we are here. We have the bicarbonate in the plasma and we are in the lung. We need to bring it back, to convert it back to CO2. The conversion back is simply reversing this reaction. So this reaction is a dual direction reaction or two-directional reaction. It means it can go in both directions. It can move from the left to the right, and it can move from the right to the left, depending on what do we need. If we need to take out CO2 and put them in the bicarbonate, then the reaction would move in this direction. If we need to bring out the CO2 from the bicarbonate, we will move in this reaction. So here in the first one, what we wanted to hide the CO2. We need to put it in the bicarbonate. That's why the reaction moved in this direction. But here we need to get the CO2 out. Okay, so we will move in the opposite direction. But before that, I need to bring the bicarbonate into the red blood cell. Okay, through what? Through the same chloride pump, right? The chloride pump will take the chloride from inside, will put it outside, and then will bring the bicarbonate inside. We reversed what happened here. So now we have this bicarbonate inside the red blood cell. There it will bind the hydrogen ion. This components will turn into carbonic acid, which will get broken into water and CO2. And now this CO2 will go out to the lung. And from there it will go to outside the body. Okay, so what happened here is that we reversed this reaction. We get the bicarbonate inside into the red blood cell, bind it with hydrogen ion. We got the carbonic acid, and then we broke it into water and CO2, and the CO2 now moved out. And we said this is the bulk of the CO2 transported in the body in form of bicarbonate. I usually say that the plasma, and this is true by the way, has a limit of CO2, okay, which is around 7%. Red blood cells also, they have limit of CO2, how much CO2 they can hold, which is around 25. So what do I do with the 70% of this CO2, with the remaining CO2? I know the numbers don't add up, okay, maybe this is 23, but anyway, the most important part is that the bulk of this CO2, since we cannot put it directly into the plasma and the red blood cells cannot take it, then I need to hide it somewhere. And the best way to hide it is to put it in a bicarbonate ion. But in order to do this, I need water, okay, and I need the enzyme, and this process would happen inside the red blood cells. Once I have the bicarbonate, I will send it to the plasma. The plasma will be fine with the bicarbonate, and sending it out, it needs a chloride pump to bring a chloride ion inside, and then in the lungs, I will reverse the reaction. Take the chloride ion out, bring the bicarbonate in, reverse the reaction, get the CO2 and move it out. Okay, so I will stop here. In the following video, we will talk about some implications of this and some lung diseases.